Hello everyone. This video will be on the 3.17 section of the IBAA curriculum. Please pause the video for a second to look at the concepts, contents, and formulae for this section. One sentence that summarizes this section is, combine three vectors to get a plane. So in the previous videos, we looked at vectors, vector products, and lines. We're going to combine these knowledge and skills together to build a brand new concept, a plane. A plane is similar to line. It's a flat surface across a 3D space. A desk that you may be working on is a plane. A screen you're watching this video, if it is not a curved monitor or a phone, is a plane. Well now, how do we make it is our main question. If you look at the formula, you may find it extremely similar to that of a line. And you're right, the only add-on to the line equation is the plus mu c, where mu is another parameter and c is another direction vector. Wait, what? What does that another direction vector mean? Well, we must acknowledge one fact that using two non-parallel vectors, we can represent any points in that plane. Or in other words, two non-parallel vectors can create a plane. A good example of this would be using the base vector. We can represent any points on a 2D world using the combination of two base vectors, I and j. And we can simply use an ordered pair, which is a trivial application using the base vectors, to represent a point. And this is true for any other planes, whether it be xy plane, yz plane, or planes that are tilted. And we just need to specify the position and identify two vectors that are on the plane. So perhaps I can draw a plane like this, and this plane could have a point like this, and then it could have two vectors that are on the plane. Okay, so at this position, this point A will give us the position vector A, and then this vector could be the vector B, and this vector could be the vector C. Now let's try an example using the vector equation of a plane. So in this case, my position vector will be 1, -2, and 3. And I'll have my lambda, which is a parameter vector, a parameter, and 2, 0, -1 will be the direction, my first direction vector. Mu will be my second parameter, and 0, 1, 2 will be my second direction vector. Now let's talk about the second formula, the equation of a plane using the normal vector. A normal vector, by the way, is a concept that seems so normally easy, but a bit more significant and complicated than that. A normal means perpendicular, but in a 3D setting. Try to stand a pencil upright on your table. Then the pencil is normal to your vector. Does that make sense? But how do we get a normal vector? Well, that's why we learned the vector product. If we have two direction vectors on the plane, then we can use the vector product of the two vectors to find a vector that is perpendicular to both of the vectors. Then this vector must be normal to the plane. So in this case, my normal vector, maybe I can draw it out like this, where the relationship with both of these vectors are perpendicular. And let's try that for the example that I gave here. So what we should do is to find a vector product of two of my direction vectors. So it'll be 2, 0, -1, the vector product with 0, 1, and 2. And let's use the formula, the vector product formula. So what I should do is do v2 w3, which is 0 times 2, so it'll be 0. And then v3 times w2 will be -1 times 1, so it'll be -1. V3 times W1 should be 0. Is it -1 times 0, so it's 0. And then V1 times W3 would be 2 times 2, so 4. V1 times W2 would be 2 times 1, so 2. And V2 times W1 should be 0 times 0, so 0. So therefore we get 1 and 4 and 2, 1, -4, and 2. And that's my normal vector. So in this case, in the formula, the n represents the normal vector, which is the vector product of B and C, of the previous one. Okay then what? And as you can see, we should do a scalar product with n on both sides. Okay, do you see that? On the left-hand side, we did r dot n, and then the right-hand side, we should find the scalar product of a plus lambda b plus mu c with n. So let's do that. So my right-hand side will be r dot n equals, it'll be 1, negative 2, 3, plus lambda 2, negative 1 plus mu 0, 1, 2. And we everything that with the scalar product of 1, negative 4, and 2. And before we do that, we have to remember that the vector product of two vectors is perpendicular to the two vectors, which means that the scalar product of the vector product with either of the two vectors will be 0. So my right-hand side, my second and third term will be 0, so we can get r dot n equals 1, negative 2, and 3 dot 1, negative 4, and 2, which is simply the same as a times n, a dot n, and which is what we want in our formula. Lastly, let's look at the Cartesian equation. This is an odd one here because there's no variable, no vector, no nothing, but just scalars and x, y, and z. And you can approach this equation from the previous equation. The left-hand side is simply the expansion of the r dot n, where r I can write it as x, y, z, and my n I can write it as a, b, and c. The right-hand side is a dot n, but it is represented as a single number d because there are no variables for that side. So I'll write it as something like a1, more like ax, ay, az, dot a, b, and c. Okay, so my left-hand side becomes ax plus by plus cz. And the right-hand side, let's just use the example above. So a dot n will be 1, negative 2, 3 dot n, negative 2. So it'll be 1 plus 8 plus 6. So, and then left-hand side, I can replace a, b, and c as well with the normal vector. So it'll be x minus 4y plus 2z equals 1 plus 8 plus 6, so it's 15. One thing to be careful here is that a on the Cartesian equation and a on the normal vector equation are different. IB differentiates them by putting a bold sign, so be careful with that. As mentioned in the earlier videos, it is important that we know how to use various forms of equations and convert one to the other. For example, once you're given a Cartesian equation of a plane, you can easily spot the normal vector of the plane by looking at the a, b, and c values. So from there, I can extract the fact that n, the normal vector, is 1, negative 4, and 2. And you can do this for any other Cartesian equations of a plane. To finish off the video, let's try one question. Let's say I give you points a, 5, negative 3, and 2, and b, 9, negative 10, and negative 3, and c, negative 3, 11, and 12. Your task is to find an equation of a plane with a, b, and c on it. And the first one will be in the vector equation. And then you'll find the normal vector equation. And lastly, you'll find Cartesian equation. All right. I hope you enjoyed this video and try some questions in this section to really master the skills that we have learned. Anyways, I'll see you in the next video. Best wishes.